Hello everybody, my name is Laura Lander and I'm a postdoctoral research associate in the Electrochemical Science and Engineering group at Imperial College London under the supervision of Greg Offer and Jacqueline Edge. My research focus lies in the sustainability and techno-economics of lithium-ion batteries. And today I would like to present a study on how we can reduce the cost and carbon footprint of EV lithium-ion batteries through efficient thermal management systems. Even though lithium-ion batteries play a crucial part in our efforts to decarbonize the transport sector, they come with their own environmental impacts along the value chain. These include, for instance, greenhouse gas emissions occurring through electricity production, toxic chemicals used for materials processing, water and energy consumption, and material depletion. The question is now, how can we reduce the overall battery environmental footprint? Here, key strategies are the implementation of environmentally friendly battery production and recycling processes and the integration of low-carbon electricity. But also, a prolonged battery lifetime can significantly reduce the overall footprint, as an extended use phase can compensate for environmental impacts occurring during battery manufacturing, for instance. Sophisticated engineering solutions can help to extend the battery lifetime and thus the use phase. In this study, we were especially interested in thermal management systems, which ensure an optimum cell operating temperature and therefore reduce adverse temperature effects and slow down battery degradation. Our aim was to establish a correlation between the thermal management system, battery lifetime, and cost and environmental footprint of EV lithium-ion batteries. We focused on air cooling as well as on liquid cooling systems, where the latter can be distinguished between surface cooling, tap cooling, and immersion cooling. To be able to quantify the impact of battery lifetime on the economic and environmental impacts of EV lithium-ion batteries, we developed carbon footprint and lifecycle cost models which take into account the battery lifetime, in our case the total distance driven during the lifetime of a battery. They further take into account the cost and carbon footprint of the electricity production, of the vehicle production, and of the maintenance occurring during the use phase. To model the cycle lifetime for a specific battery pack, in our case an NMC111 graphite pack, combined with a specific thermal management system, we firstly derived the maximum cell temperature for each thermal management system using the heat generation Q and the cell cooling coefficient introduced previously by Hales et al. The results are shown in this table here, where we can see that air cooling has the highest maximum cell temperature and surface and immersion cooling the lowest. The maximum cell temperature was then implemented in this Arrhenius type equation to model the relative capacity fate. As shown here in the figure, air cooling gives the lowest cycle lifetime, whereas surface and immersion cooling have the highest cycle lifetime. The respective input data for the carbon footprint and cost of electricity, maintenance, and vehicle production is shown in this table here. And the data was obtained from literature, publicly available data, or the EcoInvent database. The battery pack cost was calculated using BatPack. These graphs here show the overall lifecycle cost and carbon footprint for the various thermal management systems, where it is further distinguished between the contribution of the battery production, vehicle production, electricity used for charging, and maintenance. Comparing the results of our lifecycle cost and carbon footprint calculations, to grasp the extent of impact of battery lifetime on cost and carbon footprint compared to other parameters, we conducted a sensitivity analysis where besides the lifetime, also the cost and carbon footprint of electricity and battery pack production are varied. It is shown that by doubling the battery lifetime, the lifecycle cost can be reduced by 33% and the carbon footprint by 23%. To reduce the overall battery carbon footprint, also the electricity footprint plays a significant role. On the other hand, battery pack production has only marginal impact on both carbon footprint and lifecycle cost. A 70% reduction of battery pack production leads to only a 10% lifecycle cost reduction, and an 80% pack carbon footprint reduction to only 19% reduction of the overall carbon footprint. We further wanted to assess how a modified cell design can improve the efficiency for tap cooling and in return lifetime, cost, and carbon footprint. Tap cooling has the inherent advantage towards surface cooling that the cell temperature gradient is lower, therefore reducing battery degradation. However, the cell used in this study does not allow for an optimal functioning of tap cooling, and therefore does not reflect the positive impact of tap cooling on the cycle lifetime. We therefore performed a comparison of the degradation rate for two different cell designs. One is the COCAM cell, which is more suitable for tap cooling, and one is the A123 cell, which is similar to the cell used in the first part of the study, and which is more suitable for surface cooling. Indeed, the lowest degradation rate is observed for the COCAM cell combined with tap cooling, where the lifetime can be increased by 36% compared to the surface-cooled cell. Implementing the cycle lifetime for the optimized tap cooling system in our life cycle cost and carbon footprint models, we can see that the life cycle cost and carbon footprint for the optimized tap cooling system can be significantly reduced compared to the non-optimized system. Moreover, the life cycle cost and carbon footprint can be reduced by 40 and 30%. To conclude this study, we could show that an efficient thermal management system with extended battery lifetime has a significant impact on the environmental footprint and life cycle cost of lithium-ion batteries in EV applications. Switching from air cooling to surface cooling, for instance, can decrease the carbon footprint and life cycle cost by 25 and 27% respectively. Performing tap cooling on a modified cell design decreases the carbon footprint and life cycle cost even further by 35 and 40%. We could further show in our sensitivity analysis that battery lifetime extension is key to achieve cost and carbon footprint reduction. On the other hand, battery pack production, for instance, has only a marginal impact. Moreover, the integration of low-carbon energy sources is crucial to increase the environmental benefits of EVs along the value chain. In summary, we could demonstrate that engineering solutions such as thermal management systems are a swift strategy to increase the overall battery sustainability and economic viability. At this point, I would like to thank you very much for listening to this video and for your attention. And if you would like to learn about the study in more detail, please find below the paper reference. I am further very much looking forward to answering your questions during the Q&A panel on April 30th. Thank you very much.